Thank you for viewing this technology presentation of Control Technology Incorporated. The CTI difference is very simply stated: rock-solid performance, timeless compatibility. In this presentation, we will introduce you to the 2500P ACP1 application coprocessor and to the Workbench Integrated Development Environment for IEC 61131. The last 10 years have witnessed dramatic evolutionary changes in the 2500 series system. Before 2007, CTI was a supplier of compatible I/O and communications products for the SIMATIC TI-505 system, one of the world's premier process control platforms. CTI believes in the continuous evolution of this legendary product line and is dedicated to keeping its legacy alive with smart enhancements and rich features that help our customers run their plants as safely, efficiently, and seamlessly as possible. The introduction of our family of CPUs in 2007 was a key technology that enabled us to modernize and broaden the product. Today, the 2500 series system includes solutions that reach from the device layer through the control layer and into the supervisory layer. At the device layer, we have conventional wired I/O bases in both classic and compact sizes that communicate over remote I/O and Profibus DP. We can also attach third-party devices on Profibus, Modbus, and Ethernet IP. 2500 series Slice I/O allows you to deploy small blocks of I/O remotely over any Ethernet media. Our classic 2500 series PLC system is the workhorse at the control layer, but a new family of compact CPUs in development will offer a smaller footprint control option. 2500 series HMI touch panels allow operator interaction with the running process. At the supervisory layer, Xenon SCADA servers in both single and redundant configurations provide process visualization and data acquisition. SCADA clients can reside anywhere on the supervisory network, and a new SCADA web server product in development will allow any Windows-based browser to work as an operator workstation. In this webinar, we will introduce the concept of advanced function modules and the 2500P ACP1 application coprocessor. You'll get an overview of how the ACP1 works. Then we'll introduce you to the CTI Workbench Integrated Development Environment using a hands-on demonstration of a real project using the key features of Workbench. The SIMATIC TI-505 architecture had limited capability for backplane communication of large amounts of data as needed for today's data-intensive applications. In 2012, CTI solved this limitation with the introduction of the high-speed backplane and advanced function modules. Our new high-speed backplane, shipping since 2013, has an extra row of connectors at the bottom. This new high-speed channel provides an independent 100 megabit communications interface between the CPU and each of the first 8 slots. Advanced function modules communicate to the CPU using a 100 megabit per second Ethernet channel. That Ethernet channel is provided today using a patch cable from the module to the CTI CPU Ethernet port. Up to 8 advanced function modules can be attached to a CPU. In the future, the Ethernet channel will be located on the hardware backplane. At the end of each PLC scan, a time slice is provided for highly optimized communication to advanced function modules. The ACP1 application coprocessor is programmable instead of fixed function like the 2500P ECC1. It programs using the new CTI Workbench Integrated Development Environment for IEC 61131. Process data is exchanged between the RLL program on the host PLC and the Workbench program using either a high-density word interface for legacy TI-505 systems, an Ethernet patch cable for today's CTI CPUs, or a high-speed backplane channel in the future. The application coprocessor also supports Ethernet communications to external devices. It includes a CAMP client for connection to other CTI CPUs and 2572A modules. It includes a Modbus client and server with both Ethernet and serial capability. It includes ASCII communications over the serial port. And finally, it includes a network data exchange communication using publish and subscribe directly to other 2500p ACP1 or ECC1 modules. Support for Ethernet IP communications is coming in early 2015. Instructions are included in Workbench which allow data logging to the SD card under control of the program and automatic transfer of the data files to an external FTP server. Applications envisioned for the ACP1 include emission monitoring, gas flow calculations, turbine control, automatic loop tuning, multivariable control, and data logging and archiving. How does the 2500p-ACP1 work? The main RLL program in the PLC and the Workbench program in the ACP1 run asynchronously from each other. At the end of each PLC scan, the two modules communicate to update shared variables in the two systems. What are the advantages of using the ACP1 application coprocessor? First, it allows you to move extensive or time-consuming calculations to a separate processor. Its much more extensive instruction set gives you new capabilities that are not possible using the existing TI-RLL or SF programs. It allows you to experiment and begin a migration to IEC 61131 without having to re-engineer your process program. Program or process expansions can be added in IEC 61131 using the coprocessor. For validated processes, no changes to the existing program means little or no revalidation is required. Finally, the program source can be stored on the module, eliminating the confusion that often happens when trying to find the latest version of a program. The Workbench development model uses a PC to develop, compile, simulate, and debug the program. You can work on many programs at once, and you can run multiple instances of Workbench simultaneously. The compiled program is downloaded to the module over Ethernet. You can also debug directly on the target. You have full version control and verification on the target. Source code can be stored on the target. Online change is supported. And execution speed is 4 to 6 times faster than a comparable workshop program running on a 2500 C400. Now let's move into a demonstration of Workbench. For this demonstration, we have two PLC systems interconnected over Ethernet. The first PLC has both an ECC1 and an ACP1 which we'll be using. The second PLC has an ECC1 and a 2572 Ethernet module. For our demonstration, we'll use the ACP1 to read V50 from CPU A, multiply the value by 2, and put the result back in V51 of CPU A. Then we'll create a counter in the ACP1 which increments on every cycle of the Workbench program. We'll write the value of that counter to V52 in CPU A using a data cache connection, and we'll write the value of that counter to V52 in CPU B using a CAMP client connection communicating to the 2572 Ethernet port. So let's move into the hands-on demo portion of the webinar. We'll get started by opening Workbench. Workbench uses a container called a workspace to hold the projects we're working on. So the first thing we'll do is open our workspace. The workspace contains one or more projects. Within each project, you can use a flexible hierarchy of folders to organize the various elements that make up the project. This is the main editing area for programs, I/O configurations, watch lists, and other parts of the project. The variable editor is used for declaring and editing instances and variables. This window contains tabs for selecting program instructions, variable definitions, and SPI lists. The output window reports messages from compiles and other operations and includes tabs for accessing debug functions and diagnostic tools. The status bar shows the connection status and IP address of the target system. To do our demo project, we'll close this workspace and start with a clean sheet of paper. First, we'll create a new project. Let's call it ACP1_demo. In this dialog box, we can select the default language for this project. The selection here isn't that important because we can select the language later for each program we add to the project. We'll use structured text for this example. Then we need to assign the IP address of the target system. For this demo, it's 172.18.9.152. Select Finish to exit this dialog box. Here we can select the different field bus communications that will be used in the project. We can also add that later, so we'll skip it here. If we're connected to the network where the target system is located, we can verify communications from this dialog box and retrieve the firmware version of the module. Having the firmware version will allow the compiler to warn us if we try to use features that aren't supported by that firmware. Having collected all the information, the project framework is now created using a template for the ACP1. The first thing we'll do is create the variables that will be needed for our demo. We go to the variable editing window. Click on Global since we will define these as global variables. Right-click and select Insert Variable. We'll name this one to CPU_A_V51 to hold the value that we're going to write to V51 in CPU A. This variable will be an integer. Then create another variable and name it from CPU_A_V50 to hold the value that we're going to read from V50 in CPU A. This variable is also an integer. Finally, create a variable named counter, which will increment on every program cycle. Now we've created all the variables that are needed for our demonstration. Next, we'll create the programs that are needed for incrementing our counter and for multiplying the value we read from V50 in the CPU. Let's create a new program in structured text to increment the value of the counter variable on every scan. Highlight the Programs folder, right-click, and select Insert New Program. We'll call the program Incrementer. Select Structured Text and leave the Main Program Radio button checked. Press OK. Now the program has been created. Double-click on the program to open the editing window. Now we'll use the structured text syntax to add 1 to the value of the counter on each scan through the program. Next, we'll create a function block diagram program to multiply the value read from PLC memory location V50 by 2. Highlight the Programs folder, right-click, and select Insert New Program. We'll call the program Multiplier. Select FBD and leave the Main Program Radio button checked. Press OK. Double-click on the program to open the editing window. Now we'll insert a multiply function block from the list. Set one input to the variable we created that contains the value of V50. Set the other input to 2, and set the output to the variable we created that will be written into V51. That completes the program. So now we have our variables created and our programs created. The last thing we need to do is enter a field bus configuration to handle reading and writing the variables to the PLCs. To enter the field bus configuration, click on the icon to open the field bus editor. Click on Insert New Configuration and select CTI 2500 Data Cache. This is a special field bus connection which uses the high-speed interface to the ACP1's host CPU. Click Insert Master Port, and now enter the IP address of our host PLC, which is 172.18.9.140. Click Insert Slave Data Block. We'll keep the default setting of vMemory and enter our starting address, which will be V50. We're reading from the PLC, so we keep the default for the cache direction setting. Now click OK. Next, we need to specify the variable for containing the information read from V50. Click on the Insert Variable icon, then double-click where the question marks are. Now we can select our From CPU variable name from the list, then OK to exit these dialogues. Now we repeat this process for the variable that we're going to write back to V51. Insert Slave Data Block, enter the starting address of 51, and this time it will be a write to the PLC. Now insert variable and select our To CPU variable from the list. Finally, we'll insert another slave data block to write the counter value to V52. To address V52, and it's a write to the PLC. Insert the variable and select counter from the list. That completes the field bus configuration needed to handle all the communications with CPU A. Now we have one more configuration to create to allow us to write the value of the counter over to CPU B through the 2572A Ethernet module. Insert a new configuration. This time select Camp Client. Insert a master port and enter the IP address of our 2572A, which is 172.18.9.155. Insert a slave data block. Camp always reads and writes vMemory, so we only have to enter the starting address, which is V52. Then insert variable and select counter from the list. That completes our field bus configuration for this project. All that remains is to compile our project, download to the target, and test. To compile, we simply click the compile icon. When the compile is complete, we verify there are no errors. So now we're ready to download the project to the target. To download, first we connect to the ACP1. It asks us if we want to download the application. Click Yes, and the download is completed. Then, simply click the Run icon to start the application. You can see that our counter immediately begins incrementing. Workbench allows you to view the variable in multiple windows. We can see the values in the field bus window, or in the variable window, or in the program windows. Now let's switch over to Workshop to verify the communication with the PLCs. First, we'll connect with PLC A. Open a chart and load a template I've previously created with the values we're interested in. As you can see, our counter value is being written into V52. And if we change V50, we can see that the multiply program in the ACP1 is doing its job, and the result is being returned to V51. Now we'll close the connection to PLC A and connect to PLC B. Open a chart and load a template I've previously created with the values we're interested in. As you can see, our counter value is being written into V52. We've successfully created our first ACP1 project, which did calculations and exchanged data with two PLCs. Total time, about 10 minutes. Now we'll close with a quick summary. To summarize what we've seen in this presentation, the 2500P ACP1 is an important bridge product that lets you develop process extensions using a feature-rich IEC 61131 programming environment. This allows you to experiment and begin a migration to IEC 61131 without having to re-engineer your process control program. Workbench is a new, modern process automation development tool that gives you a new option for programming the 2500 series system. Future CTI CPUs will support development using Workbench, and support for RLL using Workshop will also continue. The CTI commitment to you. We employ the best of today's technology while emphasizing simplicity and ease of use. We build on your existing investment to minimize the risk and cost of change. We connect you to best-in-class solutions, and we offer you highly personalized customer service while still maintaining our global reach. Thanks for taking the time to view this introduction to the ACP1 application coprocessor and the Workbench integrated development environment. We appreciate your interest in CTI products and look forward to serving you in the future.